Picture two people sitting across the table from each other, desperate to communicate, but with absolutely no shared language between them. And we are not talking about something as straightforward as English and French. We are talking about two modes of existence so fundamentally different that they might as well belong to separate universes entirely. The first person speaks classical computing, zeros and ones, transistors, binary logic gates, the same foundational digital language that has driven every single computer built on this planet for the past 7 decades. The second person speaks something far stranger, the language of quantum mechanics, superposition, entanglement, qubits, probability distributions, calculations that do not just exist in one state, but in many states simultaneously, all at once, until the moment you look at them. For an extraordinarily long stretch of computing history, these two worlds had no way to reach each other. A quantum processor placed right beside the most powerful classical supercomputer ever built might as well have been sitting on a different planet. There was no interpreter. There was no shared channel. There was no bridge. A quantum diplomat with nothing to say and no one who could hear it anyway. And then NVIDIA entered the room with exactly that bridge. They called it NVLink. They unveiled it in October of 2025. And now, as we cross the 1-year mark since that announcement, the entire computing world is sitting with a single question that actually matters. Did it work? The answer, as it turns out, is not simply yes. The answer is yes in ways that genuinely surprised even the people who built it. And by the time you finish reading every word of this, you will understand precisely what unfolded, why it carries the weight that it does, and where this entire trajectory is heading from here. To truly grasp why NVLink represents such a seismic shift, you need to understand the problem it was engineered to solve. Not at the surface level that most technology coverage stops at, but at the level where the actual physics lives. Quantum computers are, in principle, staggeringly powerful machines. They process information using qubits, and unlike the classical bits you are reading about in the first paragraph, qubits do not have to choose between 0 and 1. They can exist in superposition, occupying both states simultaneously until measurement forces them to commit. This means a quantum system can explore an almost incomprehensibly large number of potential solutions to a given problem at the same time. Layer on top of that the phenomenon of entanglement, where two qubits become so deeply linked that the behavior of one instantaneously determines something about the other regardless of how far apart they are. And you begin to see why researchers have spent decades believing quantum computing would eventually transform entire industries. Simulating molecular interactions, cracking open optimization problems that classical machines choke on, training machine learning architectures in ways that conventional processors simply cannot replicate. The theoretical advantage is real, and it is enormous. The practical problem is that qubits are extraordinarily fragile. They maintain their quantum properties only under conditions that are almost comically difficult to sustain in the real world. A tiny temperature fluctuation, a stray electromagnetic signal, even vibration from the environment around the machine. Any of these can destroy what is called quantum coherence, collapsing the quantum state and turning the computation into noise before it ever produces a meaningful result. This vulnerability is why quantum error correction is not just a nice feature to have. It is the entire game. If you cannot detect and repair errors in real time, while the quantum processor is actively running, the computation falls apart. Full stop. And here's the part that makes quantum error correction so brutally difficult to achieve. It has to happen at microsecond timescales. The quantum processor generates errors continuously. The correction cycle has to close faster than new errors can pile up on top of the old ones. On a standalone quantum processor without classical computing support running alongside it, this is essentially impossible to pull off reliably. What you actually need is a classical supercomputer sitting in intimate proximity to the quantum processor, running sophisticated error correction algorithms in real time, sending correction signals back to the quantum processing unit fast enough that the quantum calculation never loses its footing. That is the exact gap NVIDIA built NVLink to close. And once you understand that, everything that followed makes a particular kind of sense. NVIDIA made the formal announcement of NVLink on October the 28th, 2025 at GTC, Washington, D.C. Jensen Huang himself delivered it, and his choice of framing was careful and deliberate. He described NVLink as the Rosetta Stone connecting quantum and classical supercomputers, fusing them into one unified system, and marking what he called the onset of the quantum GPU computing era. He made a statement at that event that arguably deserved far more attention than it received. He said that in the near future, every NVIDIA GPU scientific supercomputer would be a hybrid system, tightly coupled with quantum processors, to expand what computing is capable of doing. Not select supercomputers, not specialized research facilities. Every GPU scientific supercomputer on the planet would eventually carry a quantum processor connected to it. That is the breadth of transformation NVIDIA is positioning itself to drive. But press conferences are not results. Announcements are not achievements. So let us walk through precisely what the 12 months following that announcement actually produced, because the gap between what was promised and what was delivered is worth examining carefully. The first move NVIDIA made after the launch announcement was immediate, and it revealed a great deal about their strategy. Rather than keeping NVLink proprietary and tightly controlled, they opened it up to partners from day one, and the partners they attracted were not minor names. 17 quantum hardware builders signed on from the start. Companies like IonQ, Rigetti, CQC, and Silicon Quantum Computing joined, covering a wide spectrum of qubit architectures, including superconducting systems, trapped ion platforms, spin qubits, photonic approaches, and neutral atom designs. This was a strategically critical decision. NVIDIA did not engineer NVLink to function exclusively with one style of quantum computer. They built it as a universal interconnect, a single coherent system capable of linking GPU supercomputing power to any quantum processor, regardless of the underlying technology it relied on. 5 quantum control system builders also came aboard, including QCarl, Qubit Control, and Zurich Instruments, whose hardware handles the physical translation of signals between the quantum processor and the classical computer. 9 of the most important scientific institutions in the United States joined the initiative immediately as well. Brookhaven National Laboratory, Fermilab, Lawrence Berkeley National Laboratory, Los Alamos National Laboratory, MIT Lincoln Laboratory, Oak Ridge National Laboratory, Pacific Northwest National Laboratory, and Sandia National Laboratories. These institutions are not curiosity partners. These are the organizations that developed nuclear technology, decoded the human genome, and operate the fastest supercomputers accessible to open scientific research anywhere in the world. Their immediate participation sent a message to the entire global scientific community that NVLink was serious infrastructure, not a marketing exercise. By November 2025, less than 4 weeks after the launch, the momentum had already spread well beyond American borders. NVIDIA announced that more than a dozen supercomputing centers and national research institutions across Europe and Asia had joined the program. What had begun as a US-led engineering initiative became a globally coordinated infrastructure build within a single month. And that was the moment the first real benchmark arrived, and it shattered records. Quantinuum, one of the most technically respected quantum computing companies operating today, integrated their Helios quantum processor with NVIDIA GPUs through NVLink. And the result of that integration was something that had never been accomplished before in the entire history of quantum computing. They demonstrated the world's first real-time use of a scalable decoder for a category of quantum error correction codes, known as QLDPC codes. To understand why this result lands with the weight it does, you need to know what QLDPC codes actually are. QLDPC stands for Quantum Low Density Parity Check Codes. This is a class of error correction approach that theoretical researchers had believed for years could be substantially more efficient than the surface codes that most quantum computers in operation today rely on. The theoretical case for QLDPC was well established. The problem was always implementation. Running QLDPC decoding in genuine real time, fast enough to actually keep pace with the rate at which qubit errors accumulate, had seemed so computationally demanding that many researchers doubted it could be done under practical operating conditions. NVLink did it with a round-trip error correction time of 67 microseconds, 67 millionths of a second from error detection to correction signal sent. The Helios quantum processor required a reaction time of 2 milliseconds to function correctly. NVLink was 32 times faster than that requirement, not faster by a narrow margin, 32 times faster. That is not clearing the bar. That is clearing the bar by an enormous distance and leaving room to scale dramatically further before hitting any ceiling. The technical specifications that made this possible are worth laying out in concrete terms because they explain why NVLink succeeded where every previous attempt had fallen short. The system delivers 40 petaflops of artificial intelligence performance at FP4 precision. Its GPU to quantum processor data throughput reaches 400 gigabits per second. And its latency, the time required for a signal to travel from the GPU to the quantum processor and return, sits below 4 microseconds, 4 millionths of a second for a complete round trip. This was achieved through a networking approach called RDMA, over converged Ethernet, which allows the GPU to read and write directly to the quantum control system's memory without routing the data through the main CPU. This eliminates an enormous source of delay and keeps the correction loop closing at the speeds quantum error correction demands. Because it is built on standard Ethernet infrastructure rather than exotic proprietary cabling, it is also genuinely scalable in practical deployment environments. The engineering insight embedded in this is worth sitting with for a moment. NVIDIA solved a problem that the entire field had assumed would require highly specialized custom hardware, and they solved it using networking technology that already exists and has already been proven reliable at massive scale. That is a hallmark of engineering that actually works in the real world. As the calendar turned from 2025 into 2026, the ecosystem forming around NVLink began expanding in ways that showed just how seriously the broader quantum research community was taking what NVIDIA had built. At GTC 2026 in March, the scale of CUDA-Q adoption, the software platform that runs on top of NVLink and provides developers with the tools to write hybrid quantum classical applications, became visible in a way it had not been before. Scaleway, a major European cloud provider, began supporting CUDA-Q on its quantum as a service platform, enabling execution across hardware from Alpine Quantum Technologies. PsiQuantum integrated CUDA-Q with its construction platform for simulating large-scale fault-tolerant hybrid applications at scales that were not previously reachable. Pascal integrated CUDA-Q with its quantum resource management interface, enabling coordinated scheduling of work across its quantum processors and accelerated computing infrastructure. TII integrated its Chibok framework with CUDA-Q for hybrid workload validation. And AMMQ announced an extensible distributed quantum compiler built on CUDA-Q, demonstrating how hybrid applications could be distributed across multiple quantum processors simultaneously, simulating computational workloads at scales that would have been out of reach just 12 months earlier. And then Seneca and Chipu Quantum ran something that stopped researchers around the world mid-conversation. They executed what is believed to be the largest known state vector simulation of a quantum optimization routine ever performed, a 43-qubit simulation of a novel algorithm called quantum enhanced memetic taboo search, running across 2048 NVIDIA Ampere GPUs. This targeted a challenging category of combinatorial optimization problems called low autocorrelation binary sequences, which have direct practical applications in signal processing and communication systems. The scale of classical simulation supporting quantum algorithm development demonstrated by that run made it impossible to argue that CUDA-Q and NVLink were still theoretical constructs. They were producing real results at the absolute frontier of what any computing system had previously done. In April 2026, NVIDIA took a step that almost nobody had anticipated, and it may ultimately prove to be the most consequential single move they made during the entire first year of NVLink. They launched Ising. Named after the Ising model from statistical mechanics, a theoretical framework that fundamentally transformed the mathematical understanding of complex physical systems, NVIDIA Ising is the world's first family of open-source artificial intelligence models built specifically for quantum computing applications. The results it delivered were striking in ways that went well beyond what the press releases conveyed. The Ising toolkit was designed to directly address two of the most debilitating bottlenecks that have slowed the practical deployment of quantum computers since the very beginning. The first is calibration. Every quantum processor requires regular and intensive calibration to keep its qubits behaving in a consistent and predictable way. As quantum systems grow larger and more architecturally complex, calibration becomes an enormous drain on time and human expertise. Bringing a large quantum system from an unstable state back to a properly tuned operating condition can take days of work by teams of researchers with deep specialization in quantum hardware. Ising calibration addresses this directly. It is a 35 billion parameter vision language model capable of reading experimental measurements from a quantum processor and automatically inferring the precise adjustments needed to bring the system back into alignment. With an AI agent running Ising calibration, the time required to move a quantum processor from an unstable state to full operational readiness drops from days to hours. This is not an incremental efficiency improvement. This is a transformation in the operational economics of running quantum hardware. The difference between a quantum computer that spends most of its time sitting idle waiting to be calibrated and one that runs research continuously is not just a matter of cost. It is a matter of how fast the entire field can move. The second bottleneck Ising addresses is real-time error correction decoding. Ising decoding delivers performance that is up to 2.5 times faster than pi matching, the current open-source industry standard that essentially every quantum research group in the world uses for error correction. It achieves up to 3 times higher accuracy than pi matching, while requiring 10 times less training data to reach those performance levels. Those numbers represent a substantial leap beyond what the field had access to before Ising existed. And the real-world deployment data confirmed that the benchmarks were not theoretical exercises. Agik, a photonic quantum computing company with hardware installed at the UK's National Quantum Computing Centre, integrated Ising calibration into the calibration workflow of their first-generation photonic quantum computer called Artemis. The result was a 3 times reduction in the engineering time their team spent on calibration every single week. Tasks that had previously required senior quantum engineers with years of highly specialized expertise could now be carried out by non-specialists. That is a practically important result that often gets buried beneath the more technically dramatic headlines. One of the most persistent barriers to deploying quantum hardware at meaningful scale is the human expertise required to keep it running. If artificial intelligence can lower that barrier in a substantial and measurable way, if calibration can become something that does not require a quantum physics doctoral degree to perform competently, then the entire economics of quantum deployment shift. More institutions can realistically afford to operate quantum hardware. More researchers can access the machines. The pace of progress across the entire field accelerates because more people are able to contribute to it. Alongside these software and AI developments, the national laboratory deployments advanced with tangible infrastructure investments. Oak Ridge National Laboratory, home to Frontier, the world's first exascale supercomputer, and a machine that crossed the threshold of a quintillion calculations per second, partnered with NVIDIA and HPE to install an NVIDIA GB200 NVL72 system at the Oak Ridge Leadership Computing Facility in early 2026. Researchers there are using NVLink and CUDA-Q to pursue quantum error correction and hybrid quantum classical algorithms directly on site at the same facility that runs the most powerful open science supercomputer on Earth. The significance of that convergence should not be understated. Frontier broke a barrier that the entire high-performance computing community had spent years working toward. And now it shares a data center with quantum processors, connected through NVIDIA's bridge technology, contributing to what the U.S. Department of Energy has declared as a formal goal: the deployment of a scientifically useful quantum supercomputer in the United States by 2028. Pacific Northwest National Laboratory added its own significant development at GTC 2026, announcing a collaboration specifically aimed at developing tight integration between NVIDIA GH200 Grace Hopper superchips and FPGA-based quantum measurement and control systems. The PNNL team stated explicitly that their goal is to make quantum computer calculations practically useful within 5 years, and they identified NVLink as the critical connection layer that makes that timeline achievable rather than aspirational. It is worth taking a step back to understand the broader strategic position NVIDIA occupies in the quantum computing landscape, because it is genuinely different from what every other major technology company in this space is doing, and that difference is a significant part of why NVLink has performed as well as it has. Most companies competing for dominance in quantum computing are doing so by building their own quantum processors. Google has Willow. IBM has its family of superconducting quantum systems. Microsoft is pursuing a fundamentally different physical approach through topological qubits. Amazon has its own quantum hardware initiative. Each of these companies is essentially placing a bet that their specific architecture, their particular approach to building and stabilizing qubits, will ultimately emerge as the dominant technology. NVIDIA made an entirely different kind of bet. They are not building a quantum processor at all. NVIDIA is building the infrastructure layer that connects every quantum processor to classical computing power, regardless of which underlying qubit technology eventually wins the competition. This is what financial analysts have taken to calling the picks and shovel strategy, drawing on the observation that during historical gold rushes, the merchants selling mining equipment often accumulated more wealth than the prospectors actually doing the digging. CUDA-Q already integrates with approximately 75% of all publicly available quantum processors as of 2026, spanning hardware from IonQ, Rigetti, IQM, and numerous others. NVLink supports superconducting, trapped ion, spin qubit, photonic, and neutral atom architectures simultaneously. NVIDIA profits from the growth of the quantum computing market, regardless of which architecture ultimately prevails. And in the meantime, they are the entity making all of those architectures more capable by connecting them to GPU supercomputing resources that dramatically expand what each of them can accomplish. The total addressable quantum computing market is projected to reach $16.3 billion by 2030, growing from under $1 billion in 2025. NVIDIA's infrastructure-centric model positions them to capture a meaningful share of that growth across the entire ecosystem, rather than betting everything on a single technical horse. The geopolitical dimensions of NVLink's first year are also worth engaging with seriously, because they reveal that what NVIDIA built is not just commercially important, but strategically significant at a national level. When U.S. Secretary of Energy Chris Wright commented publicly on the NVLink announcement, his language was pointed. He described maintaining America's leadership in high-performance computing as requiring exactly this kind of bridge to the next era of computing, accelerated quantum supercomputing. He identified the collaboration between national laboratories, emerging companies, and established industry partners like NVIDIA as central to that mission. And in December 2025, when Undersecretary for Science, Dr. Dario Gil testified before the House Science Committee, he described the convergence of artificial intelligence, high-performance computing, and quantum systems as placing the country on the edge of a genuine scientific revolution. He outlined an initiative called the Genesis Mission, a federal effort to mobilize national laboratories, industry partners, and academic institutions to construct an integrated discovery platform capable of doubling the nation's research and development productivity within 10 years. The framing was unambiguous. Artificial intelligence and quantum computing are no longer separate technological threads. They are the foundational elements of a new category of supercomputer. And the bridge between them, NVLink, is infrastructure that the United States federal government considers central to its competitive position globally. China, Europe, Japan, and South Korea are all watching this development closely. The global supercomputing centers that signed on to NVLink within weeks of its launch were not doing so because they were curious about a press release. They were doing so because they understood that access to GPU quantum hybrid infrastructure will determine which research institutions can operate at the genuine frontier of discovery in the coming decade. The nations and institutions that build out this hybrid infrastructure early will carry a meaningful advantage into every field that quantum computation eventually touches, from materials science and pharmaceutical development to climate modeling and energy systems, to artificial intelligence itself and national security. The competition is no longer purely about who can build the most powerful standalone quantum processor. The competition is about who can build the integrated system in which quantum processors actually become useful at scale. And in that competition, NVIDIA spent its first year establishing NVLink as the platform that everyone else is measuring themselves against. So let us return to the question this entire story has been building toward. Did NVIDIA's quantum bridge actually work? Walk through what year one actually produced. NVLink launched with 17 quantum hardware partners and 9 U.S. national laboratories committed from the start. Within weeks, more than a dozen global supercomputing centers had adopted it. Quantinuum used NVLink to set a world record in quantum error correction, achieving real-time decoding that ran 32 times faster than the operational requirement. CUDA-Q became the dominant software layer for hybrid quantum classical computing, integrating with the overwhelming majority of publicly available quantum processors worldwide. The 43-qubit quantum optimization simulation at Seneca pushed the boundary of what hybrid classical quantum computation had ever accomplished. The Ising AI model family launched with calibration performance exceeding every general-purpose AI in its category, and error correction decoding 2.5 times faster than the previous industry standard. Real-world deployments at Oak Ridge, at Pacific Northwest National Laboratory, at the UK's National Quantum Computing Centre, and at institutions across 3 continents produced results that were concrete and measurable. Engineering time cut by a factor of 3, calibration timelines compressed from days to hours, error correction speeds exceeding operational requirements by margins of 30 and above. This is not a technology still gathering evidence that it might eventually matter. This is a technology that delivered across multiple dimensions in its first year and is now in the process of scaling across an expanding global infrastructure. What comes next is where the implications become most consequential. The U.S. Department of Energy has set 2028 as the target year for deploying a quantum supercomputer capable of solving real scientific problems that no classical machine can match. The infrastructure NVIDIA assembled in 2025 and built upon through 2026 is the foundation on which that target rests. The Ising AI models will continue to improve as more quantum hardware generates more calibration data and as more research teams refine them for their specific architectures and use cases. NVLink will become standard equipment in scientific supercomputing centers in the same way that GPU interconnects already are. And Jensen Huang's prediction will gradually shift from a bold statement made at a product launch to an observable, verifiable reality. Every major scientific supercomputer on Earth will eventually operate as a quantum GPU hybrid system, with NVLink as the connection that makes the two sides into one coherent machine. The question is no longer whether the bridge was successfully built. The bridge stands. The question is how fast the traffic moving across it grows. And based on everything that happened in the first year of its existence, the answer to that question is already faster than most people anticipated when Jensen Huang first announced it in October 2025.